key concept of this new IOMMUFD framework. So the left one is a legacy VFIO model, and there are some key concepts like VFIO container, group, and device. And device is just devices, PCI, like PCI physical PCI devices. And group is in one group, devices just each other for the DMA. So, but in most cases, in one group there are only one device, and the container is about when the application wants to set up some DMA mapping table. The container is a unit to set up the DMA page tables. So like when we want to set up one DMA mapping to the container 0 in this sphere, so the related DMA page tables will be set up for device 0, device 1, device 2. So all the DMA mapping will be done for all devices in the same container. So this is a key concept in the legacy VFIO, most about the DMA. And so the right figure is talking about some new concept in the IOMMUFD and IOMMUFD framework. You can see that the device is not changed, so it's the same concept. And the group, it turns from the black to the gray because from the user space application perspective, they can't see the group concept anymore. It is hidden by the kernel. So in the kernel, the group concept is still there. Just as I talked about the concept. So, and a new concept called IOAS, which is IO address space. So this concept is very similar to the legacy container concept. So the unit of setup DMA table entries. And also there one concept IOMMUFD is handle for manage multiple IO address spaces. And so to summarize, the main difference is group is hidden by the kernel, and container is turned to the IO address space, and there's one new IOMMUFD to manage multiple IO address space. Okay, so in this page, we will see from the user space application level, like DPDK, how the interface is changed. So the left one is still the legacy VFIO, and the right one is IOMMUFD plus VFIO Chardev framework. And so let's first see the right one, the left one. The blue block is user space interface, like in legacy VFIO, there are multiple VFIO interface. So container group device is part of it, and under that's VFIO module, and also IOMMU driver. There could be different IOMMU driver for different vendors, and so from the application level, we use the VFIO interface to manage the device DMA, intrust, MMI, etc. So this is the legacy one, and the new one, this split the interface into two parts, as we talked. So the IOMMUFD interface. So this is the standalone IOMMU subsystems. So it's mainly for the DMA management. So the IOMMUFD interface mainly for DMA. So under the interface, it's actually an IOMMU driver in the kernel, and also the VFIO interface is changed because it only has the DMA part. So it only has interrupt and IO extra. So the VFIO PCI driver is still there. And so this is about the user interface. And to make it more clear, I will use a VFIO example to show how the application will be changed. Like the last one is still the legacy VFIO, so similar code is still also existing in DPDK, and we can see that first step is for legacy one we will create a new VFIO container to open the DB VFIO to get the container on the descriptor. Then we will find the IOMMU group of specific device. So here we use this device, physical design device for an example. And we find the IOMMU group of this device, and we open that to get the group FD. And we add the group to the container using the VFIO group and container this UAPI. And then we will get the device file descriptor using the VFIO group get device FD. And to notice that we use the PCI BDF number as an identifier to get the device file descriptor. And so when we want to set up one DMA entry, we need to input those information to kernel, like the virtual address, the IO virtual address. This is process virtual address, and this is IO virtual address, and the size. This example is 1 page, and the flags, do you allow DMA reads or DMA write or both? And also, then you will use VFIO IOMMU map DMA. This UAPI to set up one DMA application table entry. So this is how VFIO application use the legacy VFIO to set up DMA entry for device. And the right one is how the code is changed to IOMMUFD plus VFIO Chardev, how it works for the same DMA mapping. And so first you need to open the IOMMUFD, and then you need to open IOMMUFD, you need to open this DVMU. This is created by the IOMMU framework. And you need to allocate an IO address space using the IOMMU IOAS lock, this UAPI, and get the IO address space ID. So this ID will be used later. And to get the device ID is a bit different, because here we will not use the BDF number. We will use one string under the VFIO devices. So there will be one short device under this folder for one maybe a physical design device. So to get this directory, you can use this physical this VDF number to find this directory. But to open the device FT, you need to use this folder, this directory. So if you want to bind the device then you need to bind the device to IOMMUFD using this VFIO device bind IOMMUFD. And binding to it, after binding to IOMMUFD, you also need to bind the attached device to IO address space using this UAPI also. And Then, if you want to set up the DMA mapping, besides the information in legacy VFIO, you need to include the IO address space ID, which is created when you allocate an IO address space, and the size of the arguments in the flag is very similar. And the UAPI is changed to IOMMU IOAS map. It's a different name. So this is the UAPI example, and I think maybe it's more clear to see how the VFIO application will change when after introducing the two frameworks. And then I will talk about one question is how is world in DPDK. So we all know that there are two words that have some VFIO related codes, like the VFIO-based buses. So like PASID bus, and also recently there are more buses to include VFIO support. And also, EAL is part of VFIO-related code. So these two parts need to support both legacy VFIO and IOMMUFD plus VFIO Chardev. So why to support both? Because currently, in latest kernel, so these two modes are both supported, but in the long term, only the IOMMUFD plus VFIO Chardev, this mode will be supported in the kernel. So after some time, the legacy VFIO will be dropped. But currently, if we want to use it in DPDK, we need to support both. And as you PASID bus will go first, and it also brings us one question that how the application choose to use this new framework, because only applications that want to use new features will want to use this new framework. So maybe IOMMUFD can be a VA option to let the application choose. And but this is open question, and I think we could discuss in community and when the RC comes. And the second point is the physical buses like BCI should be able to take the virtual VFIO PASID devices. Because in last page we see that the device identifier turned from the PDF to a string like VFIO0, that is the device identifier. So vendors could generate some the VFIO Chardev that is not backed by a physical PASID device. That means when the DPDK application sees a VFIO PASID device, that may not have a VDF number because that is virtual device. So if we want to include these virtual VFIO PASID devices, we cannot rely on PCI bus SFS because as we see, like in PASID buses, we rely on this PCI bus SFS to get information of the PCI device. But when the device is virtual, we don't have those SFS to rely on. So, but that could be solved by using VFIO API to get information, like to get those information in devices configuration space, like that. And the final point is what changes will be introduced to PNDs. So I assume these changes will be very minimal, because we may introduce some bus level API changes into different like PASID bus. When that changes happen, PND also needs change, because most PND are PCI based, so they may need to change. But So I think this bus API change will be very minor. So I suppose this BMD change is also very minimum. So yeah. So next, my colleague Yahui will introduce more details of these two frameworks and how DPD will use those two frameworks. Yahui?
Okay, so yeah, I'll share my screen. Okay, my screen. Okay, yeah. So just now Chenbo had introduced some background about why we need legacy, why we need to transferring from legacy of PCI into the IOMMUFD. Later, he also mentioned about we're in this layer, in this new framework, we can also allow some virtual PCI device type that is the result Chardev not physical. So we can investigate some more deep dive into these details in this part. Okay, so yeah, let's start looking at this. So I will introduce this whole picture as the time sequence. So normally when we starting Linux with the PCI card plug, so Linux will find there's a PCI card plugin, and then it will create a PCI software presentation, which is the PCI tab, and put this in the PCI bus, in the Linux bus. So, and then normally after we want to pass through this device to this place, so we will bind this PCI device with the generic PCI, like the DPDK, EV bind, scripture, or other tools. So we are buying this with the VFIO PCI driver, and in this way, VFIO PCI driver will prop this PCI device, and then it will register a VFIO device and set up all the pass-through things needed. So whenever we register a VFIO device, for example, we register VFIO device 0, and then we will create a device presentation, and then create a char device node, and present it to the user space application. So in this way, you can see there's a /dev VFIO X, which can be defined by the application. So, and also there's a corresponding VFIO container interface, which is /dev VFIO, and which can be used for the application to set up the IOMMU page table. So, and then once we are launching the DPDK application, and in the EAL stage, actually we're trying to scan all the device which can be propped, and in that normally the DPDK will scan the standard Linux PCI bus for the PCI device. So it's in the /sysbus PCI device PDF. And you can find all the PCI device related info there, and we can scan all this. And also, whenever we apply the allow list strategy or deny list strategy, we're also by scanning all the info from this PCI SSID bus. So, and once we after this stage, we'll find the qualified device we're trying to probe, and then the DPDK will finding the corresponding char device node, which is used for this PCI device pass-through, and we find this device node, and then we open this device. Okay, so, and whenever we're trying to touch this device, there's one UAPI which is called query device info, and then that is typically trying to check what is this device type. And normally when we are using a generic PCI driver, it is trying to respond that, okay, this there's UAPI which is responding to the VFIO device /PCI, and normally we're calling this VFIO PCI type. And then, whenever when the driver TMD is trying to do the initialization, we will also need to set up the allocation table through the VFIO interface by opening this /tab VFIO. So that is the VFIO call sequence. And then, once we introduce IOMMUFD VFIO PCI, so you can see that there's some difference happening. So from the device level, you can see that on the left part, we're opening the device, and now we're opening with the new directory, which is that VFIO device, VFIO. This is different from DPDK's perspective. But if you check the underlying infrastructure, actually there's no change. Everything is almost the same. And then let's see the IOMMU part. So now we're opening the /IOMMU as the allocation table management interface. And also we're using the IOMMUFD subsystem as a bridging between the UACI and the IOMMU driver. So, as you can see, whenever the DPDK is trying to start in this new framework, so for the EL scan part, there's no change. We're still scanning the SysFS entry. We're still using the similar allow list appearance policy through this SysFS info, but we're using a different UAPI to open this device. So that is the main difference from the application perspective. Okay. So that is then now we're introducing the new model, which is in the Chenbo's part we mentioned the virtual VFIO PCI. So now before we are talking about virtual, so let's say something more about, so we may talk about the physical. So what is physical? So we're defining something new here. So normally if you see that when DPDK is trying to open the VFIO device, so it will all the access will go into the VFIO device node and finally go into the VFIO PCI driver. And once it's that this VFIO PCI driver is actually our PCI device, and this is actually a real-world PCI device. So in this way, actually, we are seeing that this VFIO device is backed by our PCI device, as that is why we call physical. And also you can see that this driver is responding that I'm also our VFIO PCI device type. So that's why we call this a VFIO PCI device and backed with a physical device. So, and then let's see what is a virtual type. So I marked there are two different places. So if you see this VFIO device part, as you can see that now in our virtual type, so actually we are creating a virtual device and then which is putting a virtual bus, and this virtual and prop them with a virtual VFIO virtual device driver, and this virtual device driver is still reporting the VFIO as a VFIO PCI type. So this is why this is still a VFIO PCI pass through, and then if you see that the EL scan part, so that is a little bit different. So because once we trying to scan all the device, so in the left part, all the device is on the Linux PCI bus, so we can find them easily. But now the device is on a virtual bus, and as you know that Linux has a lot of kinds of virtual bus, and it's not possible for DPDK to find all of them. So that we cannot find all the device info from the virtual bus, and instead now we could only find the device in another place, which is all the device node will be created under this /VFIO device VFIO-X. So by open this device and access all these devices the PCI CSR region, because all these devices, we're supposing all these devices VFIO PCI type, and then we can access these devices PCI CSR and get their product ID and vendor ID. So by getting all this info, we can find all the related info and applying our scan, allow list, and deny list strategy to make sure we find a qualified device. So let's see. So in this way, you can see that, okay, well, now we're introducing a VFIO PCI, which is the virtual VFIO PCI type, and it is still a device which is reporting as VFIO PCI type, but which is backed by a virtual device. Okay, next, and we were doing some further changes. So now, previously we talked about VFIO PCI virtual type, and now we're saying that, okay, we introduced some more changes, which is virtual backed by hardware. So I will just directly show the difference. So as you can see on the left part, this device is backed by a virtual device and still reporting as VFIO PCI type. But on the right part, as you can see that this virtual device is not an orphan node. So actually, it is a child of the real world PCI device. So in this model, you can see that it's like, okay, we have a PCI card and PCI driver, and in our driver initialization, we will create this virtual device. And we will have a corresponding VFIO virtual device driver to prove it. So from the DPDK perspective, it is still VFIO PCI type, but if you see from the underlying perspective, so it is a virtual device, but it is backed by hardware. And also you can see that this benefit is that we can grant this virtual device with the hardware capability, like DMA, so that we can say that this virtual device has DMA capability. We can let this virtual device to read and write application memory directly with high performance. And this model has quite some advantage, which we will show in the next page. So before we go to the next page, let's see that. Okay, so the virtual type is actually the VFIO device, which is backed by a purely virtual device. But the virtual type backed by hardware is actually a virtual device, which is a child of the physical device. And since it is backed by a physical device, we can grant some DMA capability. So next is one example to implement this. So it's the Intel Scalability solution. So we will give some examples. So let's see it from the bottom to the top. So now we're using the one Ethernet card, and in our PF driver. So we were once we prop this PCI device, so we are creating an auxiliary device. And in the last slide, we are saying this is a virtual bus. So now we are taking the auxiliary bus as an example. So whenever we want to create a virtual device, we create an auxiliary device, and correspondingly, we bind this device with VFIO auxiliary driver, and then register a VFIO device, which can be seen by application. Okay, so and for the fast pass, we grant them with DMA capability. So the total architecture is like, okay, let's see from slow pass and the fast pass perspective. So for the slow pass, so whenever the application wants to access this device info, touching this device, PCI, CSR, MMIO, basically it's all the driver is all the driver's response, and all these access will be intercepted by this VFIO auxiliary driver, so that we can compose a virtual device. And in our specification, this is typically called the VDCM, virtual device composition module. So this is a module to compose a virtual device, so that you can present whatever you want to the application. And for the fast pass, you can see that we grant this auxiliary device with DMA capability and directly into the user space application. But since each user space application has its own address space, so that if we want to assign a physical device, if we want to assign a physical device to multiply the application with isolated DMA protection domain, so we need to also introduce some unique ID so that this DMA can be isolated with different domain. And in this way, we introduce this PASID, which is a PCI capability, so that with this PASID, we can make sure the DMA is tagged by PASID with PCI BDF, so that the DMA is secure and won't attack other places. And this PASID is only available in the IOMMUFD framework, as Chenbo introduced in the first slide page. Okay, so there's some benefits. It's like, okay, since we're composing the control path and only need data path as hardware source, so that we can have a more scalable data path, which means we can have a higher density instance number. And also, since we're composing the control path, which means we can have a very flexible control path. We can compose whatever we want and present them to the application. And due to this benefit, so we have this can boost the DPDK startup time. So comparing to single IOV, the scalable IOV can decrease DPDK startup time by 50%, and we have a reference link here, so you can see some more detailed data showing. And also, we have presenting a presentation on the last year's DPDK summit, putting DPDK time quickly by device composition, which is also have some introduction about this DPDK startup. Okay, so now we have introduced most of the thing, and the rest of this key takeaway. So at the first, so we introduced that background. As you know, there's multiple device password framework like VFIO, vDPA, and other, and they all have some IO page table setup for the pass-through device, and all this IOMMU management logic is duplicated. And on another side, so there's also a request for the emerging IOMMU feature like PASID, DMA Page Fault, the tracking. So due to these two reasons, so the VFIO IOMMU is decoupled into the IOMMUFD and VFIO Chardev. And for the IOMMUFD, it is a standalone and unified interface, which can be consumed by VFIO, and not only by VFIO, but also by other subsystems to set up the IO page table, which is used for DMA mapping. And for the VFIO Chardev, because we introduced IOMMUFD, so there's some changes in the VFIOs happening to make VFIO can work with IOMMUFD to set up the IO page table. And then we introduced some more interesting thing which can be extended in this framework. So, and we introduced the device model. So from the first, we have the legacy VFIO PCI, which is very traditional and stable. And then we introduced IOMMUFD and VFIO PCI. And then we introduced the physical type and the virtual type. And then we introduced a new, the virtual type backed by hardware. And the Intel Scalable IOV is one of the examples to show how this virtual type backed by hardware is implemented and its advantage is shown. And since the Scalable IOV is leveraging the PASID, and the PASID is only supported by IOMMUFD framework. So we need this IOMMUFD to support this solution. Yeah, and if you have any interest, any more discussion, want to contact, please contact Chenbo and me. Thank you.